I'm actually going to record this, and anyone, and if people that are giving credit in other classes want to use that, I'll send the link along and they can do whatever they want with it later on. But thank you for the opportunity to talk about this. It's definitely a project that kind of took me by surprise. And I hope I can kind of do it justice. I think it's an interesting topic. Divisibility tests are always something that have been intriguing to me, and hopefully by the end of today, they'll be intriguing to you as well. Dr. Fry and I kind of put our heads together on this. We actually wrote a paper that was published at the beginning of this year in the College Math Journal called An Infinite Family of Divisibility Tests. And the content of this talk is essentially coming from there, okay? But in getting started, I have a little beginning exercise for us all, okay? So I want you to start thinking about place value very carefully, okay? You know, I didn't realize how complicated place value was until I had to start teaching children how it works, okay? Teaching college math classes isn't enough, but when you have to teach kids how place value works, it's more complicated than you realize. And to give you a feel for that, here is a little beginning exercise. And what I would challenge you to do is to actually go to Chuck's or wherever you go on campus to think about these sorts of things and mess around with it and see if you can carefully think your way through place value and get something from this. So here are the rules. Take any 3-digit number with the first digit larger than the last. Okay, so somebody give me one. Okay, I want to make sure that I'm not, cheating. Yes. 542. 542. So that's a 3-digit number with the leftmost digit bigger than the last. Okay, so we have 542. Okay, and then the next rule says to reverse that and subtract from the original, which would be 245. Do you guys see what I'm doing up there? Okay. Okay. And okay, we have to do a little bit of borrowing and whatnot. Of course, when you do this in general, the middle digits are always going to match, which is going to be fairly problematic because you're going to have to subtract the bigger first term from the smaller last term. Yes. So I mean, look, you can go like this. You can say that's a 3, okay, and then you can borrow from here and make that a 4, and then this becomes 13. Okay, and of course, this is now a 12. I get 7. 13 minus 4 is 9. 4 minus 2 is 2. And then I reverse that and add, apparently, according to rule number 3. And what do I get? 9, 18, and 1, 0. Hey, which is something that I said was kind of the name of the game. Yeah? That's kind of interesting. Apparently, since the name of the game is 1089, that should be what you get every single time. Okay. I would challenge you to go think about place value itself and how this works. Now, what that means is you're going to have to think about, all right, if I have a 3-digit number, it's going to be able to form 100 times something plus 10 times something plus something. Yes. And when I reverse it, the first and last terms are switching, but the middle one's staying. And then think about what happens when you borrow things, okay? And I think you'll see that there's some interesting cancellation in things that take place. Isn't that cool? I think that's cool, and I think you should go think about that, right? Just as an exercise in place value. Now, is it magic? No. There's some mathematics going on in the background. There's some nice cancellation that's happening. I did consider actually going through why it works, but I think it would be better for you to go sort of work on that yourself, okay? Are there other 1089 type games that one could come up with? Well, I would challenge you to do that as well. Try it with like 2-digit numbers and make up, rules like that the first digit has to be bigger than the last, for instance, yes? So reverse subtract, reverse the answer, then add, and see if you keep getting the same number over and over. Or try it with 4-digit numbers and see if you can kind of get a feel for how this place value business is actually working. But there are other 1089 type games. Don't go look on the internet. Go kind of come up with them yourself and see if you can establish why they are working, okay? Now, the reason I bring this up is because in order to talk about what we're going to talk about today, it really took a lot of careful thinking about place value, okay? We're going to talk about divisibility from the perspective of place value, actually. So, doing it this way, can you recall any tests from your past experience in mathematics that involved the digits of a given integer? You guys think of something like, I mean, don't think that it's dumb, okay? Can you think of something like, for instance, how can you tell if a number is divisible by 2? Anyone? Yes. Oh, right. So the last digit has to be divisible by 2, right? So the last digit has to be 0 or 2 or 4 or 6 or yes. Okay. So that is a divisibility test that involves carefully looking at the ones digit. Yes. How can you tell if something's divisible by 5? Same sort of thing. The last digit has to be a multiple of 5. Yes. Anybody know any other ones? Any other tests? 6?
No, just kidding.
Oh, okay. Well, you'll know one for 6 after this talk. Yes.
3, if you add up all the digits.
Right. So, right. So in integer, and we're talking about whole number divisibility here, okay? Like it has to go in precisely. Okay. So a whole number, an integer, is divisible by 3 precisely if the sum of its digits is divisible by 3. So there again, we're thinking about the digits themselves and coming up with some kind of divisibility rule. Yeah. And that's what I mean by a truncation-type divisibility test. Namely, you're taking the digits, you're chopping them apart, and you're doing something with them to figure out whether divisibility is occurring. Make sense? And here's the thing. If all goes well in this talk, we are actually going to find all the tests. All of them. Okay? No matter what you want to divide by or check divisibility for, we will have a way to like exhaustively talk about every single possible truncation-type divisibility test. Okay? I know that that sounds like that can't happen, but believe me, it ends up being a little bit simpler than you might realize. Okay? So here are a few divisibility tests that you might be aware of. Somebody already mentioned the one for 3. An integer is perfectly divisible by 3 if and only if, right? That's a mathematician's way of saying, you know, this is a mathematical equivalence, yes? If and only if the sum of its digits is divisible by 3. Now, why that happens to be the case is something that we'll have to kind of explore later on. But 96312 is divisible by 3 because you can easily tell, well, look, 9, that's divisible by 3, so 6. And then 3 is obviously divisible by 3. And then 1 plus 2 is divisible by 3. So therefore, the sum of all those digits is divisible by 3, right? So even though that number looks obnoxiously big, it's easy to check for that for divisibility by 3 by simply looking at the sum of its digits. Okay. Another one is that an integer is divisible by 9 if and only if the sum of its digits is divisible by 9. Okay, that's another one. If you take number theory, you'll see kind of some, you know, exercises whereby you can actually show that this is true, but you also have like some sophisticated machinery that you use and notation, things like that. We're not going to really be doing that here. We're going to actually see why this has to be true in a more basic way, okay? An integer is divisible by 11 if and only if the alternating sum of its digits is divisible by 11. What that means is you kind of break the number apart into its digits, and then you kind of take the first one minus the second one plus the third one minus etc. Does that make sense? And then you can check divisibility by doing that. Now look, like 9, 6, oh, by the way, I should have said 9 plus 6 plus 3 plus 7 plus 2, clearly that is divisible by 9, yeah? You get 27, yeah? Okay, now what about 96316? Well, if I go 9 minus 6, that's -3, yes? Or +3, plus 3 is 6, minus 1 is 5, plus 6 is 11. Ooh, that's divisible by 11. Therefore, the original thing is divisible by 11. Yeah. And 7 is a weird one. This is where things get sort of weird. Okay. And really, it was thinking carefully about 7 that I think was somewhat of the breakthrough that we needed. Okay. So basically, an integer is divisible by 7 if and only if when its last digit is truncated, that is, you chop off the last digit, and multiplied by 2 and subtracted from the rest, one gets a result that is divisible by 7. Now you might say to yourself, what? Okay, so that means I can kind of truncate this thing. So like if I start with 96313, instead I can look at 9631 minus, it said to kind of take the last digit and multiply it by 2. Does that make sense? So the last digit is 3, and I multiplied that by 2. So that means 9631 minus 6, which is, how much is that? 9625. And I said to myself, I still can't tell. So you can do it again, right? So what you do is you then take this guy and you go 962 minus 5 times 2. And what do we get? 952. And you say, still don't know. So do it again. 95 minus 2 times 2 is what? 91. Still can't tell. So what do we do now? 9 minus 1 times 2 is 7. And I definitely can tell whether that's yes. So that is what I mean by a truncation-type divisibility test, one where you actually, chunk off digits, and you maybe subtract 2 times something, or subtract some multiple of those things, or add a multiple of something, and you just kind of iterate this thing all the way until you can tell whether divisibility is happening. Make sense? All right. The question is, can we find all of them? All of them, for any number at all, okay? And surprisingly, we actually can. That's sort of the amazing thing. All right, so here's a little exercise with an eye toward finding them all. And at first, we're going to talk about prime numbers, which are numbers that are only divisible by 1 and themselves, okay? Now, 5 is not very interesting, is it? What about 2? No, okay? So let's only look at odd primes, and all that does is rule out the number 2. And we're only going to look at odd primes that are not 5. 5 is not very interesting, okay? So an odd prime that is not 5, we start off with something like that. Well, that means that P has to end in either 7 or 1 or 3 or 7 or 9, yes? If that is true, whatever P is, I don't care how obnoxiously large it is, if it ends in 1 or 9, then then basically P itself is already 1 away from a multiple of 10, isn't it? Yeah. So if P ends in 1 or 9, it's already 1 away from a multiple of 10. So there is a way to write it as 10 times something plus or minus 1. Yes? And that's going to be key. There's a way to write this as 10 times something plus or minus 1. Now, what if P ends in 3 or 7? Well, then if I multiply it by 3, that ends in 1 or 9. Yes? Okay. If I multiply P by 3, then it will then end in 1 or 9, and therefore it will be within 1 of a multiple of 10. You see what I'm saying here? Okay. These are the only possibilities. P either ends in 1 or 9, in which case it's already 1 away from a multiple of 10, or 3 times it will be within 1 of a multiple of 10. Okay? That is the key. Believe it or not, that really is the key. And what will be key is that number K that's sitting right there. Whatever K is going to determine what the divisibility test is. Okay? In fact, testing whether N is divisible by P, we will show, is equivalent to testing whether P divides Okay, what in the world is this junk right here? N minus A0 divided by 10 minus plus K times A0? Let me explain. I'm just saying, what's the first, basically we're truncating the first digit of N. That's what's happening. A0 is what I'm referring to as the first digit of this thing. If I subtract A0, it's gone. And then the last digit is now 0. So if I divide by 10, the 0 just goes away. Does that make sense? So if the last digit of the number was 7 or something like that, then I subtract 7, so that ends in 0, and then I can divide that by 10, and then that just makes the 0 go away. Yeah? So in other words, what I'm saying is, testing whether P divides N is equivalent to just getting rid of the first digit, and then basically adding or subtracting K, the same K that you got for that multiple of 10, adding or subtracting K times that first digit. Make sense? K times that one digit. How do I decide whether to add or subtract? Well, if it was 10K minus 1, then I will add K times the last digit, K times the one digit. Yeah? If it was 10K plus 1, then I will subtract K times the one digit. Yes? So I basically do the opposite of if it's plus 1, I subtract. If it's minus 1, I add. Yes? And that K right there is the key. Okay? Let's actually try this for a particular P and N. I said a prime. Okay, so somebody give me their favorite prime.
29.
49?
29.
Oh, 29. Okay. Okay. Get me word there for a minute. All right. So if P is 29, okay. Now we need to, that is already within one of a multiple of 10. Yes? So what I'm going to do is I say, well, I need to write that as 10 times something minus 1 or plus 1 in this case. Minus 1. So that's going to be 10 times what? 10 times 3 minus, oops, not minus 3. What am I writing here? Minus what?
1.
Minus 1. Yes. Okay. So that means that our K is 3. Does that make sense? And because we subtracted, the test is going to be to truncate the last digit and go plus what? Plus K times the last digit. Yes? That's it. Plus 3 times the last digit. So you just go plus 3 times the last digit. Let's actually try that for a number, okay? Let's do it with a number that we actually know 29 divides. Does that make sense? So for instance, 97, yes? Let's try it for like N equal to 97. Suppose we sat there for a minute and we said, I can't tell whether that's divisible by 29 or not. Yes? In fact, I don't think it is. Is that not?
87.
87, sorry. Let's do something that actually works. 87. Okay, so apparently what we should do is we should truncate the last digit and do what? Truncate the last digit. So you go 8, and then what do? Add or subtract? Add 7 times what? 3. So that's 8 plus 21, which is, ooh, is that divisible by 29? Yes. Okay. Yes, it is actually. Okay. And it turns out that this is something that you can immediately come up with sort of divisibility tests on the fly. You can even do this in your mind. Does that make sense? I mean, once you kind of have this in your mind, you can kind of say to yourself, well, 29, well, for crying out loud, that's like within one of a that's within one of a multiple of 10. It's 10 times 3 minus 1. That means I just add 3 times the last digit. Truncate the last digit and add 3 times it. Yes, that's it. Okay. All right, you with me so far? Okay, any questions? Why does this work? Okay, now, as happens in mathematics a lot of times, I think the original argument we gave is a lot more complicated than the one I'm about to give. Essentially, the one I'm going to give you now is kind of the reverse from the way that Dr. Fry and I actually saw it, okay? So we're going to kind of start with what we're claiming and show that indeed it is equivalent to divisibility, okay, in this way. And actually, I'm expecting everybody in the room to follow this, but I definitely expect the people that are math majors to follow this, for sure, okay? So first of all, P is not 5. It's not 2. P is an odd prime, different from 5, yes? Therefore, does P have anything in common with the number 10? No. Okay? In mathematics, we say, or in number theory, we actually say that means P is relatively prime to 10. It has no common factors with 10. Yes? Okay, so there's nothing in common with 10 whatsoever. Okay, so watch this. Either P or 3 times P is within 1 of a multiple of 10. Yes? So it's 10K plus or minus 1. Yes? So watch this. So Pj is equal to 10K plus or minus 1, where J is just 1 or 3. Okay? I'm just trying to capture both of those things in one equation here. Yes? P times something is equal to 10 times K plus or minus 1. Yes? Okay, so just watch this. P dividing evenly into this guy right here, which is the guy I'm claiming is kind of like the test. This is basically saying truncate the ones digit and then subtract or add K times the last digit. Kind of do the reverse of whether you went plus, if it was plus 1, you subtract. If it was minus 1, you add. You guys see how I'm doing minus plus and plus minus here? Yes? That means do the opposite. Okay? So if it's plus, you subtract. If it's minus, you add K times that ones digit. Now, I claim that P divides evenly into that thing if and only if P divides 10 times it. How can I make such an audacious claim? How can I claim that P will divide that thing if and only if P will divide 10 times it? Yes. Yeah, right. So P doesn't have anything in common with 10. Multiplying by 10 doesn't ruin divisibility at all. Does that make sense? Like 10 is not going to help divisibility happen, right? 10 is not helping. If I want to multiply by 10 again, it's still not going to help. The thing that's going to be the determiner of divisibility is that other thing. But now watch, if I distribute 10, look what happens. The 10s cancel, yes? And what I end up with is n minus the first digit minus plus 10K times the first digit. You see what I mean? Now what I'm going to do is I'm actually going to solve for 10K. This guy right here is literally 10K, yes? Think about it. 10K is right here, yes? If I want to solve for 10K plus or minus 1, I would have to minus plus 1 to the other side, yes? So I can actually replace 10K with what it equals, which is Pj minus plus 1. Now, here's the interesting thing. If I distribute this like plus or minus thing through, this minus plus thing through here, what about this guy and this guy? What do? They just become plus, don't you see? Yeah? So what I'm going to do is I'm going to distribute these guys from both sides. And I'm telling you, this minus plus and this minus plus just become plus. So I'm going to get minus the first digit, and then the other thing is just going to be plus the first digit, yes? And what happens to those guys? They go away. And what's left? Just the minus plus Pj times this thing, yes? You just have minus plus Pj times that first digit. Now, why is that interesting? Well, we just said P divides this thing if and only if P divides basically n minus plus P times that stuff. Well, for crying out loud, P for sure divides that stuff. Why does P for sure divide this stuff right here? Well, P's there. Yes? So the only way P is going to divide that is if P actually divides in itself. See what I'm saying? So what we've shown is that P will divide this guy if and only if P divides n, right? So when we can actually go both directions now, yes? The divisibility of n by P is equivalent to this truncation and adding, subtracting. Come on. Make sense? Now I'm telling you, the way we saw it was not that simple at first. We had all this like place value stuff. We're factoring things out. We're writing things really carefully. But it was really only in preparing for this talk that I suddenly realized, oh my goodness, this is way easier to see going in this direction. Okay, so there it is right there. I didn't even plan to show that to you guys, but since it was rather simple, I hope that kind of makes sense. If it doesn't, you can talk to me about it later. Okay, but that is basically the proof of why this is working. Okay, here's some applications. Let's look at p equal to 3. Okay. Well, 3 times 3 is equal to 10 times 1 minus 1. Yes? So here's our j right here. And what's this one? That's our k. Yes. So we have j equal to 3, k equal to 1. So since this is minus, we are going to what? Add k times the last digit. Yes? K is 1 in this case. So the truncation test in this case is going to be adding 1 times the last digit to the truncated thing, which is basically just adding the last digit. Does that make sense? Now, doesn't that sound a lot like the classical test? Classical test is you add all the digits. In some sense, this is almost more flexible than that, because here I can kind of stop at any moment. You see what I mean? I can kind of like take the last digit, add it to the rest. Yes, I can really kind of stop that process at the moment that I recognize divisibility by 3. Okay, but listen, here's the thing. There's not just one test. There's a lot more. Okay, if you're in number theory, you realize that this is an example of something called a linear Diophantine equation. There's actually infinitely many possible values for j and k. And actually, there's a pretty simple way you learn in number theory to write them all down. Yes? So you can actually come up with lots of other divisibility tests by finding different values of j and k. All right? So here it is. Here's another one. 3 times 7 is 21, correct? And that's 10 times 2 plus 1, right? And we kind of hone in on this 2 right here. That's our k. And so what's an alternative test? Well, since this is a plus 1, we can subtract 2 times the 1's digit, and that will be another truncation divisibility test for 3. Does that make sense? That sounds a lot like the divisibility test for 7. It is. Right? It's sort of strange, but that it ends up being this. There's the same thing. Divisibility test for 3, divisibility test for 7. You can test them in the same way. Interestingly, so for example, we can test whether 963 is divisible by 3 by instead kind of hacking off the 3 and subtracting twice that. Yes, 96 minus 3 times 2 is 90. And I hope that is clearly divisible by 3, yes? If you weren't sure about that, you could go one more step. You go 9 minus 0 times 2, which is 9. And that would be divisible by 3, yes? Yes. And in this way, you can find infinitely many divisibility tests for the number 3, right? So that's interesting. Okay, any questions on that? Questions? All right, continuing on. What about 7? Well, let's see. 7 times 3 is 21, yes? Which is within one of a multiple of 10. Yeah? 7 times 3 is equal to 10 times 2 plus 1. See? And so we have j equal 3, k equal to 2 here. And so immediately we realize that we get the exact same truncation test that we did for 3 in this case. And that's the classic one where you subtract twice the last digit from what remains, yes? So that's a divisibility test for 7. But there are other options. For instance, 7 times 7 is 49, right? 7 times 7 is 49. That's within one of a multiple of 10. In fact, that's 10 times 5 minus 1, right? 10 times 5 minus 1. Therefore, what would be a truncation divisibility test that we can get from that? truncate the last digit and add 5 times the last digit to what remains. That is a legitimate divisibility test for 7. Okay. So for instance, if we want to check whether 966 is divisible by 7, you can take 96 plus 6 times 5, which is 96 plus 30, which is 126. Still too hard. Okay. You truncate off 6, you add 6 times 5 to 12, and you get 42, and I'm pretty sure that's divisible by 7. Yes. If you were still concerned about that, you could truncate off the 2 and add 2 times 5, which is 10 to 4, you get 14, which is divisible by 7. Yes? And you could actually Dr. Fry did a little bit, did a lot actually at the end of our paper, that having to do with these little cycles that occur. For instance, if you get down to 14, right, if you don't know that that's divisible by 7, you could add 4 times 5, which is 21, and then you could just keep going and see what happens. You get in these little interesting orbits at times, you know, and it's like, come on, can't you tell that one of these is divisible by 7? Get it together, right? So there's some interesting mathematics that happen there as well. Now, what's interesting is someone actually emailed us pretty soon after our paper was published and noticed, or they actually asked us the question, hey, did you hear about this kid in Nigeria that found a divisibility test for 7 that involves adding 5 times the 1's digit? And so we were like, no, we hadn't heard about that. We hadn't seen that test necessarily anywhere in a textbook or anything. And it's not that hard to think about why if subtracting 2 times the 1's digit worked, that adding 5 times the 1's digit worked. But this 12-year-old apparently came up with that test on his own. And I don't know if you can see that very clearly, but over there on the right, he's kind of showing some examples of how he does his test, which is the one we just came up with, right? So interestingly, this guy, or this kid, his name is Chika Ofili, came up with this particular test. Someone drew our attention to that after the paper posted, okay? Well, here's the thing. The only thing the proof relied upon was that J and K satisfy Pj equals 10K plus or minus 1. Yes? And P had to be, what's the word? Relatively prime to 10. So does it have to be prime? No. It just has to have nothing in common with 10. Okay? So that means we can apply the same thing to even P that are not prime, so long as they are relatively prime. Yes? So let's look at 3 times 7, shall we? What about 21? Well, that one's easy because 21 times 1 is all right. 21 is already one within one of the multiple. Yes? So 21 times 1 is equal to 10 times 2 plus 1. And therefore, since it's 10 times 2 plus 1, what would be a good divisibility test for this? Subtract twice the 1's digit, and you have your truncation divisibility test. Yes, that's not that surprising that came out because we just saw that the divisibility test for 3 and the divisibility test for 7 actually had that one in common. Does that make sense? But we can come up with other ones as well. So, for instance, you know, checking that 21 divides 966. We can take 96 and subtract 6 times 2, which is 96 minus 12, which is 84. And I think 21 divides 84. Yes, we can see that really easily. If you're unsure, you could hack off 4, multiply that by 2, which is 8. What's 8 minus 8? 0. Does 21 divide 0? Yes, because 21 times 0 is 0. Yes? Okay. And there are infinitely many more that we can come up with, okay, if we just kind of carefully think this through, okay? Now, I'm just going to challenge you right now. So if you can kind of sit there with your friends, see if you can come up with a divisibility test, a truncation-type divisibility test for 17 and one for 51, okay? But don't write anything down. I'm going to demand that you come up with it in your mind, okay? So it has to be from your mind only, okay? So think about that for a couple minutes and then give me what you think. All right, who wants to give me their divisibility test for 17? I'd like to have a non-math major do it, if possible. Yeah,
Willing to try.
okay.
So I had J is 3.
Okay, so 17 times 3 is 51, right?
Then I made my K 5.
Right, so that's 10 times 5. Oops, what is it? 10 times 5
Plus 1.
plus 1. So in this case, the truncation test is going to be what?
Take the last one and subtract.
Yeah, minus 5 times the 1's digit. Yes. This is how I like to think about them. I just think about when am I adding or subtracting and what multiple of the last digit am I to. Make sense? Okay. So for instance, I don't know, let's do something that we know is divisible by 17. Like, oh, I don't know, 51. Okay. So if I take 51, then apparently I'm supposed to take minus 5 times the last digit. Oh boy, this is going to be nice, right? 5 minus 1 times 5 is 0. Check. Yeah. That thing is definitely divisible by 17. By 17. Well, what about 51? A little less interesting now that we've done that one. Okay. Okay. So what is that? 51 is 10 times 5 plus 1. It's the same test. Yes. But you could come up with other ones, couldn't you? If you really wanted to. Yeah. For instance, you could say something like 51 times 9. Oh boy. What's that? That's 459. Which is what? 46. So 10 times 46, what? Minus 1. So apparently, one possible test is to add 46 times the last digit, okay, which may not be worth our while. But nonetheless, you can come up with other tests as well. Yes? Okay. So that's interesting stuff for sure. All right. Any questions on that? By the way, we proved that all of these work. Yeah, we actually literally wrote down the proof right there. So I mean, we don't have to like question whether this is working or not. We have it on the slide if you pay a few things back. Yes, just sort of a comfort to all of us, I hope. Okay. All right. Are these okay? So here's a little thing I want to ask. Suppose someone comes up to you in Chuck's and says, hey, I have a divisibility test for this particular prime that happens to be relatively prime to 10. Yes, that's a number that happens to be relatively prime to 10. And here's what you do. You truncate the last digit and you add k times the last digit to what remains. So the question that Dr. Fry and I had in our minds was, does that test, is it accounted for in what we did? Yes? Is it something that we already had in our analysis? Yeah? And the answer to that question is, well, if we can find our J and K, then we will know it's accounted for in our tests. Yes? If there's the J and the K, we know that it's just one that happens to be in our test. Well, here's the thing. Actually, all of them are here. And here's why. So this person in Chuck's comes up to you and says, hey, my divisibility test is to truncate the last digit and add k times the last digit. Okay. Well, Dr. Fry and I say, well, okay, if that works for every single one of these, then for sure it works for n's that end in the digit 1. Yes? In fact, it works for all of them, and for sure it will end with ones that end in the digit 1, okay? So let's just choose those special n that happen to end in the digit 1. So P divides that if and only if P divides that thing right there, which because P is relatively prime, I can multiply that thing by 10 all day long and not worry about messing anything up, yes? So that will happen if and only if P divides this guy, which if you multiply through by 10, you get n minus 1 plus 10k. So this person's test is apparently equivalent to P dividing n minus 1 plus 10k. Yeah? But then P divides this, right? So this means that P will divide this, and then if I take n away, yes? If P divides n and that thing, then I could take the difference and it still divides it, which happens to be 10k minus 1, yes? So this means that P would divide 10k minus 1, which means P times something equals 10k minus 1, yes? So there is a j and a k. So that means that this thing is accounted for in the analysis that we did. There isn't some mystery truncation algorithm out there somewhere. Okay, we have them all right here. That's a little tricky to see what's going on, but believe me, if you have questions, we can come up and talk about that afterwards. Now, what if I wanted to truncate more than one digit? What if I wanted to hack off 2 at a time or 3 at a time? Yes? Fine. We can do that too. Basically, instead of dividing by 10, which is 10 to the first power, hint, truncating one digit is like truncating blocks of size 1. Then all you have to do instead is kind of, don't do like just 10, you do like 10 squared if you want to do blocks of size 2, yes? But then what you do is you then remove the last 2 digits, like the 1s and the 10s digit itself, yes? Okay. So we made up some notation for that, so we didn't have to write like a bunch of digits. We didn't want to write like A1, A0, or A2, A1, A0. We just said, well, we're just going to call that n hat. N hat is basically the last however many digits you want. Yes? Okay. If you only want to deal with one digit, n hat is that last digit. Yes? You want to deal with 2 digits at a time, n hat is those last 2 digits. Basically the remainder of n if you divide by 10 if you want 1 digit, 100 if you want 2 digits, etc. Okay? And then seriously, you just go through the exact same argument. If you want A blocks of size A, then basically all you have to do is, instead of looking for something that P is within 1 of a multiple of 10, you look for to be within 1 of a multiple of 10 to the A. So if A is 2, you look for it to be within 1 of a multiple of 100, for instance. Yes, A happens to be 2. Or if you want to hack off 3 digits at a time, that's the case where A is 3. Yes. So it's the exact same argument. There's nothing different other than the fact that I've replaced 10 with 10 to the A. Everything cancels, and you end up with this exact situation again. And of course, this guy right here is automatically divisible by P. Yes. And so P will divide that if and only if P divides n. Yeah. How it works. It's the exact same argument. So now we can actually hack off blocks of certain sizes if we want to. All right, so let's actually look at that for a minute. Okay, what about 7 times 11 times 13, which is 1001? Yeah. And what if I wanted to hack off blocks of size 3? Yeah. Well, that means I need to think of, okay, if I want to do blocks of size 3, I need to think about 10 cubed, which is 1000. I need to figure out how to get within 1 of a multiple of 1000. Well, that's easy. Here, yeah. How do I get within 1 of a multiple of 1000 in this case? Very easily, right? Because 1001 times 1 is equal to 1000 times 1 plus 1. Yes? So what will, right? So this is our K right here. This is K. This is our J. Yes? And so what are we going to do? It's going to be minus K times this in hat thing. Okay? Minus K times this in hat thing. You have to actually multiply by the last 3 digits here. So what this means is basically, in this case, K happens to be 1. Right? So it's just minus this in hat thing. So like if I wanted to check whether 1001 divides 123, 123, what could I do? Well, hack off the last 3 digits and subtract it from the rest. And look what happens. You get 0. Is that divisible by 1001? Yes. Okay. So that's interesting. And by the way, we can come up with infinitely many possible truncation algorithms in this case as well. You don't have to restrict yourself to just blocks of any particular size either. I mean, you could do blocks of size 5, 2, we'll go back to 1 if you want. Yes. This gives us a bunch more flexibility for sure. So how about this? Another little challenge for you. Come up with a divisibility test in your mind. No fair writing. Don't write it down. Try to come up with a divisibility test for 33. Okay. That involves blocks of size 2. So A equal to 2 is the block size here. Okay. Blocks of size 2. So talk about that for a minute. Yeah. All right, someone. What do you got? Yeah.
Add the last 2 digits times 1.
Okay, so how did you get that? So
I said blocks of size 2, so I'm working with 10 squared. And 33 is not within 100. So I multiplied by 3.
Yep, which got you to 99?
Nope, which is with 1 less than 100.
Yeah, so that's just 100 times 1 minus 1. Yes? And since this is our K, and this is subtracting, yes, 1. So that means we add. So you're saying you just go add 1 times in hat in this particular case, yes? Okay. So for instance, I mean, let's just try it with something that, let's just try it with something that obviously works, I guess, like 9999 or something like that. Okay. Want blocks of size 2. Apparently I can hack this thing off and just go 99 plus 99. Oh man, what is that?
198.
198. Okay. And what's interesting is you could even continue from this point. If you were like, boy, I don't know, what could you do here? 1 plus 98. And what do you get? 99. And if you don't realize that's divisible by 90 or by 33, yeah. So 99 is definitely divisible by 33. So there you go. Right. So that thing works. What about 101 and blocks of size 2? What do you got? Anyone? (101) times 1 is equal to what? 10 times, or actually, no, we did 100, right? If we want blocks of size 2. So it's 100 times 1 plus 1. So what are we going to do here? Subtract these blocks, right? Subtract off the last 2 digits, yes? Every single time. Okay, so for instance, 202, what am I going to do? 2 minus 2, which is 0, which is definitely divisible by 101, yes? So it works out. Cool. Now here's the thing. when mathematicians get going on something like this, they generally don't stop until everything is just totally obliterated. Okay. So I will tell you one last thing. I won't go through the details, but we actually dealt with the bases other than 10 as well, which give you a whole other host of divisibility tests. Yes? And it turns out that nothing really changes. You just need your thing that you're testing for divisibility by to be relatively prime to the base. So if you're working in like binary, it needs to be odd. Does that make sense? Okay, and the same exact argument goes through in this particular case. And you get a whole other class of tests that are pretty interesting. My challenge to you, and again, I'm not going to go through it right now just because I want to give you the opportunity to ask a few questions. But think about what this does in the case of binary and just blocks of size 1. Okay. So that would be my challenge to you. Go figure out the 1089 thing, figure out some other games, but also think about the case of binary. Like what does the test end up being if I just look at blocks of size 1 and I'm thinking about binary itself? Okay, turns out you get some pretty interesting things. Okay, I'm actually going to leave it at that and say thanks. By the way, there's a few little references for you, including the one that Dr. Fry and I actually wrote. One of them that I would commend to you is this one that's called Stupid Divisibility Tricks from the Math Horizons. What they have there is basically a huge collection of divisibility tests, but it's not exhaustive the way that this one is. Okay. I'll leave it at that. What questions do you have? Yeah.
Does this work for negative integers?
Sure. Well, I mean, if you want to test a negative integer for divisibility, yes, definitely does. Yeah. And I mean, I don't really see why it wouldn't work even in the case of a negative divisor as well. I think it would still work just fine. Other questions? Other questions? All right. Well, thank you very much for coming out on this Friday afternoon.
Thank you, Dr. Hammond.
Yeah.